And so we begin our review. What we're going to do first, we're going to identify different sorts of distributions. These are problems that you are given in a word problem form, but you're not sure how you want to proceed. And this is what we're going to discuss. And there are many of them that we can work with. Let's begin with a simple question. I like cards, so a normal deck of cards will be dealt from so that you receive 6 cards. Let X equal to the number of, let's make it hearts, you received. So, probability that X equals 3. What is this equal to? Well, before we even do this calculation, we have to look at the characteristics of the problem. We have to ask ourselves, what PMF is going to describe this? What PMF is going to make it reasonable for us to say, oh, this is how we calculate it? So first off, since you're being dealt 6 cards, the idea of the dealing is this is being done without replacement. And when you receive 6 cards, counting the number as an unordered, and you're doing a count. Now, it's very reasonable that if you have a PMF for this, because it's a count, you have a limitation on the values of X. I think you can have 0, 1, 2, 3, 4, 5, or 6 hearts. You can't have more hearts than the cards you've received, but you might not get any hearts. So we have a discrete and finite list of elements that can support. We're doing it without replacement, unordered count. Now, if we look at the different characteristics of the distributions we worked with, for example, the binomial, it counts things, and it counts things unordered, but it's like shaking a die or flipping a coin. There's independence from moment to moment, and this is without replacement, so that the card dealt changes what happens in the future. So the binomial would be inapplicable. Bernoulli is a single occurrence of something, that would be inapplicable. So it seems very reasonable that one of the few distributions left that count things is the hypergeometric. And now the hypergeometric was one of the very first ones that we were introduced with too. And the hypergeometric has a fairly simple form. You just have to remember it. So first off, we have to have the things of characteristic 1. Well, there are 13 hearts in your deck, so 13. Choose X as the number of ways you can get it. And next, there are the remainder set of cards that are going to be the failures, and they're the ones that account for what's left in the deck. So then if there's 13 there's, 39 failures. And since we're getting 6, you either have X successes and 6 minus X failures, or the other way around. And lastly, we have to count the total number of ways it can be drawn, and that's 52, choose 6. So it appears that we have a very reasonable expectation. So what is the probability of X equals 3? Well, it's 13, choose 3. 39, choose 3. 52, choose 6, which I could very well ask you to calculate one of these numbers out just to show me if you can do it. But there's your answer. And this is an example of the hypergeometric. Right. right, our second review problem. Let's consider the situation where it is known that calls to a switchboard occur at a rate of 55 calls per hour. You work the morning shift and we want to know the probability that you take greater than or equal to 200 calls over 4 hours. So now we look at this problem and we ask ourselves, well, what is the random variable? Well, if you let x equal to the number of calls you receive in 4 hours, then x, the values it takes on, could be 0, 1, 2, 3. We have no idea how high it goes. Maybe your phone's not working and you're taking a call every second. It hangs up second. Maybe you get huge. So there's not really a bound to x. Now, x is discrete. You're doing a count. But now, the next question you can ask yourself is, the person that called you in the beginning of the hour have anything to do with the chance of someone else calling you later? We might as well assume an independence from moment to moment. Next thing is, those calls can happen at any time during this 4-hour period. So you have a period of time from 0 up to 4. This is a continuous interval where things can land in, and you're counting within that interval. And the next thing is, things are coming in at a rate. A rate is given. Now, if you look at your distributions, you'll notice that very few of them have this infinite possibility. The geometric does, but the geometric is counting something else. You're looking for just when. What's the probability when it finally fails, or when you finally get a male in the family? It's a tree. And it doesn't look like that. But it does have this type of thing, and it does have independence from moment to moment, but it doesn't have a fixed period of time, and you're not given a rate of failure, so it doesn't meet these conditions. Now, the negative binomial has the same reason we can throw it out. So that one's gone. Well, we can pretty much say it's not hypergeometric, since we just looked at the hypergeometric. And the hypergeometric, it required a non-replacement, and I don't see where the replacement here, or non-replacement, really comes into play. So it appears to be a Poisson. Now the Poisson requires us to have a lambda. And now this lambda needs to be adjusted to the rate over the period of the time of the problem. Since the problem runs for 4 hours, your rate is given to be 55 calls an hour. You need to adjust that to 220 calls per shift for over 4 hours. Now that we have lambda, now we just say, can we write down the Poisson distribution directly? Right? So I happen to like to write P of x equals x as e to the minus lambda lambda to the x over x factorial, and put in lambda later, not put it into that formula. Now, the probability that you're going to take your x will be greater than equal to 200 is an infinite long summation. And I suspect you guys know how to do it. You can do the complement of it if you like. You can also write it as 1 minus the probability that x is less than or equal to 199. That's a finite summation. I actually think the infinite summation is easier. Let's write this out. This is a sum from x equals 200 to infinity of e to the minus lambda, lambda to the x, over x factorial. I'm going to actually write a couple of terms out for this to help you along. So e to the minus lambda, lambda to the 200 factorial, plus e to the minus lambda, lambda to the 201 over 201 factorial, etc. And you plug in lambda equals 220. Now, is there a way to reduce this? Is there a way to calculate it? Well, there's clearly a way to do this one. You can write down 200 terms, 0 up to 199, add them all up, plug it in, or you can come up with a calculus method of determining this value. This is why in the back of the book we have the cumulative distribution for the Poisson for various values. This is not one of the ones that is in the back of the book, so it's much more difficult to calculate, but the cumulative distribution in the appendix of the book is where you're going to find solutions to your Poisson problems. I'm happy with this answer, I'm happy with that answer, if you spell out how the solution looks. All right, here's the Poisson. All right, a review on problems. Sam. Consider an experiment where we are harvesting a bioproduct. And we assume a massively large collection, such as houseflies. And what we're doing is we're collecting these houseflies and we're taking a look if it has a gene that makes it have a propensity to carry a very specific type of disease. We assume the incidence of the gene is approximately 1.01 or 1%. What is the probability? We have to sample 100 flies to find our first sample of a fly with this gene. All right, once again, this is a question where the random variable isn't given to you, so you have to design a random variable and describe it in such a way that you understand what the support of the probability might be. And so figuring out what to say x is how about we refer to x to be the number of the fly we just sampled. So we sample one fly, then we sample a second fly, then we sample a third fly. That's the numbers we assign to them. And we want that fly that we just sampled to have the gene we're looking for. So, we grab a fly, we sample and say, does it have that gene? So, when we do it this way, X could be the first fly we meet. X could be the second fly we meet. X could be the third fly we meet, etc. forever. I don't know how long it's going to take. So again, I have a discrete values for X starting at 1 but goes on forever. Now, why did we say that we have a massively large collection of houseflies? Well, I don't want to change my probability from moment to moment. When I kill one housefly, I'm sure another housefly is being born someplace and we have some sort of a stable population. And so I personally believe that we assume the incidence of the gene is 1%, and that's happening each and every time we sample. So it looks like we have a probability of 1/100th for something called a success, that we find a gene, and therefore 1 minus p would be 99 out of 100 for a failure. And it looks like we repeat this Bernoulli experiment, where the Bernoulli experiment is grab one fly, what's the probability that it is carrying that gene? So we have a repetitive Bernoulli, but it stops at success. So the binomial wouldn't apply because the binomial counts the number of successes. We stop at our very first success. A picture of this looks like this, which should trigger immediately that this is the geometric distribution. So, the geometric distribution says that f of x equals 1p and then 1 minus p, and then comes, you want it to occur at the x trial, but there was 1p in there, so that's x minus 1. So that's our distribution. So what's the probability you have to sample 100 flies to find our first gene? Well, f of 100 is 1/100th, 99 to the 100th to the 99th power. Now, I like questions that change a number into at least or at most. So this is one of the few problems that I'm going to put a variant here. What's the probability we must sample at least 100 flies? Well, that's the sum of those probabilities where x starts at 100 and goes forever. So if we put this in there, p times 1 minus p to the x minus 1, the sum from x equals 100 to infinity, we get p times 1 minus p to the 99 plus p times 1 minus p to the 100 plus p times 1 minus p to the 101st. And this is a very nice expression. There's a p in common everywhere. There's a 1 minus p in common everywhere. And what's left is then 1 plus 1 minus p plus 1 minus p squared forever. That's the whole reason this is called the geometric. This is p times 1 minus p to the 99. And the sum of the geometric of 1 plus r squared plus r cubed is 1 over 1 minus r. The answer is q to the 99th. 1 minus p to the 99th. All right. Good example, hopefully, of the geometric distribution.